Hello, my name is Brandon Enright, and in this video, I would like to give an intuitive understanding, or rather an intuitive proof, of why a single twisted piece on a Rubik's Cube is not possible. So, for example, you will never run into that situation on a Rubik's Cube. You will also never run into a single edge twisted, and this is true of almost every twisty puzzle. So you'll never run into a single edge flipped on the Megaminx, or a single corner twisted on the Megaminx, or the same on the helicopter cube. You'll never have a single corner twisted there either. And it's in general a universal property of twisty puzzles. And I want to provide an intuitive, or let's say less mathematical, explanation for why that is the case. Now, if you look online and you look for, this question's been asked many times. Here's one particular place. Why is a single corner twist not valid on a Rubik's Cube? And you see here's the question. It's an easy question to understand for anyone who's familiar with any twisty puzzles. And here's the answer. So the answer starts with, okay, I'll give a group theoretic answer. And there's where the problem starts. Because if you scroll through this answer, you'll see, a bunch of relatively complicated mathematical notation, the idea of the set of stickers and the number of, permutations of, the way you could assemble the cube, that sort of thing. So then you'll see things like the cyclic group get defined, and you'll see, some definition of, some special labeling of the stickers on the corners, and then, so another definition gets made, of who knows what, and then, there's a lot of talk about like the group homomorphism, the action of the group on a particular set of pieces, etc. Right? This is a mathematically correct explanation that is just not intuitive. It's not easy to understand this explanation. And this is not the only place where you'll run into that. I have a book here, Adventures in Group Theory. I very much like this book. I have learned a lot from it. And if you turn to page 219, chapter 11, it starts talking about the legal Rubik's Cube group. And to understand sort of the legal Rubik's Cube group, you need to understand sort of what's illegal, things like a single corner twisted. And as the chapter progresses, right, you'll see a bunch of, labels occur. And these labels seem maybe like they're arbitrary. And you'll see a table of numbers. And then, the formal definitions begin. And the only way you're ever going to understand this sort of stuff is either by reading the whole previous portion of the book, or most of it anyways, or having some sort of formal background in discrete mathematics and group theory, or abstract algebra, that sort of thing. You see things like the semi-direct product and the wreath product and the sign of a permutation, and it's just frankly complicated. And I don't want to give you a complicated answer. So I'm going to try to give a sort of minimally mathematical answer, sort of tickle your intuition for why this is the case. So the first thing we should look at is, well, let's look at what happens when you turn a single face on a Rubik's Cube. And so if we turn this a quarter turn, and we ask ourselves, did any corner get twisted? Well, let's look. We make a turn, and it doesn't really look like any corners twisting. Right? Corners are moving. This corner moves here, this corner moves here, this corner moves here, this corner moves here, 4 cycle, but you don't really see them twist, right? So, if we keep on going around, where does the twisting happen? Or on this face, right? So now we've looked at the white face, now we're going to look at the green face, and we look at, it doesn't look like any corners are twisting. But now I'm going to perform a sequence on this puzzle using only the white face and only the green face. And we just looked at those two faces. And we sort of, each move that we do on those faces, it doesn't really look like any corner is being twisted. But I'm going to use only those two in a sequence we call soon, or a sequence that, Rubik's Cube enthusiasts call soon. And then we'll look at the result. So green face, white face, green face, white face, green face, white face around, and then, right, whatever. I only turned the green face and the white face. Now, if we look here, this corner, the white, orange, green corner, it's in its correct spot, right? This is the white, green, orange faces, but it's been twisted clockwise, right? And so I can sort of force the puzzle twist counterclockwise. And the same is true of this corner, right? It's also been twisted clockwise, so I can twist it counterclockwise. And then the same is true of this corner. I can twist it counterclockwise, which obviously what I was just doing is not a legal move on the puzzle. I'm just exploiting sort of the mechanics of this sort of very, very, very loose Rubik's Cube. So what was going on? When we look at, the turn of a white face and when we look at the turn of a green face, it sure didn't look like any twisting was occurring, but somehow some combination of turning the white face and the green face and corners were getting twisted. And so let me show you that sort of your definitions are all sort of relative. Whether a corner is or isn't getting twisted is sort of relative. So if we look at a green, we look at the white face, and here's the green face up here. So we perform a quarter turn. This corner moves there. And it doesn't look like it's getting twisted. And if we look at the green face and we perform this move, the same corner is moving to the same position. And again, from this perspective, it doesn't look like it's being twisted. However, if we look at, the white face and we look at the green move, we see that the way that the corner is moving is different than the way it moves this way, right? This is, I think, obvious. But if we say that this is not twisting, then we can't also say that this is not twisting, because from the perspective of the white face, it is twisting. So if you sort of declare, the move that you perform on the white face to not twist any corners, that's necessarily going to force some of the adjacent faces. And so what I mean by adjacent are the faces that share edges with the white face. That's going to force you to declare that a similar move on those faces does twist the corners, even if from sort of the perspective of that face or relative to that face, it doesn't look like they're being twisted. So that's what I mean by sort of the definition of what is or isn't being twisted is just all sort of relative, and it's in, if you define it one way, it sort of forces other definitions on the puzzle, and just as long as you're careful, it's all, consistent. So how can we know for sure that a single corner twisted on this puzzle is not possible? Because as we've already seen, this stuff is complicated, right? Turning this face, okay, none of the corners are twisting, but boy, turning this one, some corners are being twisted, like which ones are being twisted, how many, and how do we know for sure that, some combination of turning all 6 of these faces isn't going to allow a single corner to result in, end up being twisted? And it really all comes down to a couple of basic facts. So first of all, this puzzle, it's a cube, and there's 24 orientations to the cube, right? I can spin this puzzle in place, and so let's actually count them. So there's 6 faces, and we can put any of those 6 faces on top, okay? And each face is a square, and we can orient it in 4 ways. And so 6 times 4 is 24. There's 24 possible orientations of this cube in space. And if we took all the stickers off, we didn't have all these nice colors, we wouldn't be able to tell any of those orientations apart. And so if we look at and can decide that for any one face, assuming all the moves are the same, if any one face sort of has some restriction on its moves, then sort of by symmetry, all the faces will have the same restriction on their moves. So we really only need to look at one face. We'll just pick one. We'll look at white in this case. And if we can somehow determine that white is not allowing, the turn of a white face is never going to allow a single corner to be twisted, then we can say that none of the faces, turning none of the faces is going to allow a single corner to be twisted, and therefore no combination of them is ever going to allow a corner to be twisted. And so how can we do that? So this is the crux of the intuition is based on effectively one simple fact about a move. On a Rubik's Cube, a move has order 4. So what I mean by that is if we turn this face a quarter turn, and we do that 4 times, it's back to nothing. Nothing has happened, right? So in group theory parlance, the turn of a face is called an element of a group, or in this case it would be a generator. Generators are just elements of the group, but we have 6 generators available to us. And the order of that element is 4, meaning if you apply it 4 times, it's as though nothing happened. You're back to what we call the identity of the group, which is the solved state. Nothing has changed. So there's sort of your group theory parlance there. There's this property that by turning something 4 times, or by turning something on the Rubik's Cube 4 times, nothing has happened, is going to sort of allow us to intuitively see that the same is true on the Megaminx and the Helicopter Cube and really all the other puzzles that you see here. You're going to be able to see that a single piece twisted is not possible, or at least a single of a certain type of pieces. So we're going to look at the pieces where the permutation of the pieces, so in this case corners, the length of the permutation is equal to the order of the move. And so we have 4 corners, and so we know that's a 4 cycle, so the length of that cycle is 4, and we know that the order of the sequence is 4, so that's the requirement for this definition. The pieces that violate that requirement on this puzzle are like things like the centerpiece, right? So we know that a face turn is order 4, but this is just being one cycled, right? It's only one piece being permuted, and so the length of the permutation does not match the order of the face. So we can't say anything about whether or not twist is going to be constrained for centerpieces. And the same is going to be true on, this is a pentultimate, right? And we can look at the centers here. And yes, 5 go, so yes, the order of a face turn on the pentultimate is order 5. And yes, you do have 5 of these centers go around, in a 5 cycle, but you also have this one center that's just being one cycled. And so not all of the permutations of these pieces are of the same length as the order of the face move. So we're not going to be able to say anything about whether or not twist is constrained for pieces like that. And the same is true for this hybrid puzzle, which turns like a Rubik's Cube, but also allows turns of the corners. So, Rubik's Cube, order 4 face moves, and corners go in 4 cycles, so the lengths of the cycles match. And corner turns, order 3 moves. No, not face moves, they're corner moves, but order 3. But this corner is being twisted in a 1 cycle, right? It's the only thing being permuted in this orbit. And so, the length of that is 1, and the order is 3, and so they don't match, so we're not going to be able to say anything about corner, well, that's not actually true. I mean, clearly twist is not constrained for this puzzle. So we're not going to be able to sort of say that it is constrained, because it violates sort of the fundamental requirement of this, which is that the, order of a move matches the length of the cycles. And so this is, when we look at the corners here, we're going to be able to say, look, no twist of a corner, no twist of a corner in isolation is going to be possible. The same is going to be true. We're going to be able to say the same thing for the edges, because the edges also go around in a 4 cycle. 4 is the same length as the order of the move. And so we're also going to be able to say eventually that the twist of an edge is not possible in isolation, right? So you're never going to be able to get into a situation where only a single edge has been flipped. So now let's start talking about how we're going to sort of show that. We know that, if we track what happens to a single corner as we turn it around 4 times, we know that it has to end up back in its position with, no twisting. Nothing has happened to it because that's equivalent to not performing any move at all. And so whatever happens to it in the process, if it, say, gets twisted, it's going to have to at some point get untwisted. Or we can have a situation where we say it gets twisted once, and it gets twisted twice, then it gets twisted a third time. And remember, because this is all sort of modulo 3, twisting a corner 3 times is the same thing as not twisting it. 1, 2, 3, it's back to where it was. And so any of that's sort of going to be possible. So let's take a look at that. I have a whiteboard here, and I'm going to have to apologize in advance for how bad my handwriting is, but let's look at some of the possibilities. So first, let's say that we'll assign a number to the total twist mod 3. And so we have some move, M, and we're going to apply that move 4 times. And we know that that is always going to be equal to or congruent to a constant. We'll just call it 0 for this, simplify things here. And that's all mod 3 for the corners. For the edges, it would all be, 0 mod 2 because the corners only twist twice instead of 3 times. But we know some move times 4 is congruent to 0 mod 3. So there's this nice little feature of modular arithmetic where we can sort of reduce all of the constants. And so in this case, we can reduce this 4 to a 1 because 4 mod 3 is 1. And so we can say a move applied once is going to be concurrent to 0, meaning that even an individual move on the Rubik's Cube cannot twist any piece, or cannot so let's be clear here. When we're talking about, this number mod 3, we're not talking about the twist of any one piece. We're talking about the total twist of all of the pieces on the puzzle. That has to be constant, mod 3. Even after a single move. I think that's sufficient to be a proof on the Rubik's Cube, but I don't think that, this little modular arithmetic reduction that we did is actually, say, all that intuitive. But it's going to allow us to sort of make a table of what all the twist possibilities are for a single move. So we know that a single move, whatever happens to an individual corner, in total, all the way around, has to be 0. And so we can call call a clock. So no twist, we'll call that no twist. We'll call that 0. Clockwise, we'll call that 1, or sometimes like +1. And then counterclockwise, I'll just abbreviate that to C. We can call that 2, or alternatively, we can call this 0 +1 -1. This is the +1 mod, so +1 is congruent, 2 is congruent to -1 mod 3. Not important. So because we're concerning ourselves with what happens to the twist of pieces, we don't have to we don't need to be able to look at a corner and say, oh, is this corner twisted or not? And a lot of definitions or a lot of proofs that show that twist is constrained sort of get caught up on defining the twist of each individual corner. Let's just look at what happens to the twist of corners as we do moves. And so sort of the most obvious possibility is, and I'll draw a square here, and we can label the corners. We'll call this corner 1, corner 2, corner 3, and corner 4, and I won't need to label these corners anymore after this. We don't have to say, okay, well, this corner starts out clockwise or starts out counterclockwise, and what happens to it. We can just simplify this to say, well, as the corner, as the move is done, corner 1 moves into position 2, and then corner 2 moves into position 3, and corner 3 moves into position 4, and corner 4 moves into position 1. What happens to them along the edge? And so sort of the simplest case, the simplest definition is nothing happens to them. So we'll just label this all as zeros, right? So that means that no twist is occurring. And that's what we looked at when we first looked at, what happens when we turn a face. Well, we say, okay, well, none of the corners are really being twisted here. That's the 0, 0, 0, 0 situation. And when we looked at the green face, we also said the same thing, like it looks like it's 0, 0, 0, 0. But, when I did that soon move where I only turned the white and green faces, somehow corners got twisted. And so, if we define this face to be 0, nothing happens as we do that move. Then when we look at when we look at the green face and we look at the same move on the corner, we're going to have to define that as being twisted in some way, either clockwise or counterclockwise. And it doesn't actually matter whether we define, +1 as clockwise or -1 as clockwise. It just doesn't matter. And that's what I have this mirror in the back here for. I want to show you that if we look at a mirror, everything's sort of all backwards. I think this is pretty obvious, but so we have a corner on this puzzle. We're going to look at there's a bright one, it's easy to see. We're going to look at the pink, green, yellow corner. So I'm going to turn it clockwise, and I think you can agree in the video that I've turned it clockwise here, right? So pink this way, green this way, yellow this way. But if we go and look at that same move in a mirror here, now it looks like it's been turned counterclockwise, right? So the pink went around the other way, the green went around the other way, the yellow went around the other way. And so in a mirror, I'm sorry I bumped my camera, in a mirror, it's all backwards. But I think you can agree that if it is possible to have a single corner twisted, then you'll be able to see that, whether it's the single corner is twistable clockwise or single corner is twistable counterclockwise, you'll be able to see that in a mirror. It'll look different, but it just means that the choice of clockwise versus counterclockwise is totally interchangeable. It does not matter at all. And that's going to allow us to simplify our table a little bit. And so let's make this table. So, the all zeros is one possibility. Let's look at another possibility. So we could say this could be +1, and then +1, and then +1, and then 0. And I think you can agree that as a corner goes around, as this corner, clockwise once, clockwise twice, clockwise a third time, it's back to not being twisted. And then the final leg, it doesn't get twisted, right? So that's all of this sums up to 0 mod 3. This is effectively equivalent to the -1, -1, -1 case, again, because in the mirror, everything's all backwards. They're all interchangeable. And also because the puzzle is rotationally symmetric about a face, fourfold rotationally symmetric, it doesn't matter how we define this, right? So we could just find +1, +1, +1, 0. So that is effectively equivalent, I'll call it congruent to this position right here, which is +1, 0, +1, +1. So we don't have to look at this case because this one covers it. So what are some other possibilities here? So there's another one, which is +1, -1, +1, -1 is a possibility. And +1, +1, -1, -1 is a possibility. And let's see what else. So +1, 0, -1, 0 is a possibility. And I think there's probably one more, which is +1, -1, 0, 0. I believe that this table, the zeros, the 3 plus 1s, the 2 plus 1s opposite each other and the 2 minus 1s opposite each other, the 2 plus 1s adjacent to each other, the 2 minus 1s adjacent to each other, or the plus 1 minus 1 opposite each other and zeros opposite each other, or the plus 1 minus 1, right? Like this is a table of all of the possibilities. And so if you have any pattern that isn't one of these, then when you apply the move 4 times, you will no longer be back to where you started from. And so that's sort of the critical insight, that these are the only possibilities. And you'll see that each one of them has a balance. The number of clockwise and counterclockwise turns always cancels, or the number of clockwise or counterclockwise turns is always a multiple of 3, which is the same thing as it canceling itself, right? And so that's this case right here. The plus 1 plus 1 plus 1 is the same thing as no twist occurring. So because these are the only possibilities for individual moves, and none of these have any imbalance. They never result in sort of a total twist of +1 or total twist of -1. Then an individual move on the Rubik's Cube can never change the total twist of a puzzle. Now, that might not be totally satisfactory, because we kept on looking at what happens to a corner as we go around 4 times. But let's just pick one of these. We'll pick this one here, the +1 +1 +1 situation. So after we do a single move, this corner will be twisted, right? It doesn't look like it's twisted, but by our definition, it is twisted, as we did a single move. And it only gets back to where it was fully untwisted after we do 4 moves, right? So it gets twisted once, twisted twice, twisted 3 times. This is all per our definition here. And then this doesn't do any twist, and now it's back to where it started, right? And so that's because we looked at one corner when this move was applied 4 times, right? That's this port right here. You know, one corner, well, this whole move applied 4 times, no twist. But sorry again, I bumped my camera. We don't have to look at what happens to one corner when the move is applied 4 times. We can actually look at 4 corners when the move is applied 1 time. So I'm going to do that. I'm going to do this move. Okay, so we know that the corner that was here is now here, and it got twisted once. The corner that was here got moved here, and it got twisted once. So now we have 2 twists. And then the corner that was here got moved here, and it twisted once. Now we have 3 twists. And then the corner that was here moved here, and it was not twisted, right? And so again, the total twist after a single move is 3, and 3 mod 3 is equivalent to no total twist, right? So even though each individual corner got twisted clockwise once, in our case a +1, or counterclockwise in a mirror, even though it doesn't look like it, the total twist is conserved. And so that is it. That's the intuitive understanding of this. And so let me try to sort of say it a little bit more concisely, or a little bit more compactly. I'll just effectively say it again. On a twisty puzzle, in this case the Rubik's Cube, when we look at the order of a move, if the pieces, if you just pick a piece type, if that piece type, it always is in cycles of the same length as the order of that move, so in the case of the Rubik's Cube, 4, then twist is going to be conserved. And the reason twist is going to be conserved is that when you apply that move the same number of times as its order, in the Rubik's Cube case, 4, you know that it will be as though nothing occurred on the puzzle. And because nothing occurred on the puzzle when applied 4 times. Also, nothing can occur on the puzzle when the move is applied. So no total twist can occur on the puzzle, even when the move is applied just 1 time. And the reason for that is that when you look at the move applied 4 times in the case of Rubik's Cube, 5 times in the case of this, or 3 times in the case of some other puzzles, right? So the order of the move. When you look at what happens to a corner, you can say, well, maybe it got twisted, maybe it didn't get twisted, but we know that after applying it, the same order as the number of moves, it will go back to where it was. It will not be twisted. We can sort of look instead at what happens to 1 corner when applied 4 times. We can look at what happens to 4 corners when applied 1 time. And so when we do that, again, it's as though you're looking at what happens to 1 corner 4 times, only now you're looking at 4 corners 1 time. But what would happen to this corner when it moves from here to here? So, okay, it's right here. And we care about what happens when it's going to move from here to here. Well, that's after 1 move. Now something's going to happen to it on our second move. That's effectively equivalent to what happens to this corner on the first move, right? And so there's nothing fundamentally different about all these corners. I think you can agree that all the corners are effectively interchangeable. And so instead of having to track what happens to this corner when we move it around 4 times, we can simply look at what happens to each one of the 4 corners when it's moved once. And since we know that nothing happens to this corner when moved 4 times, we know that the total net effect of what happens to all 4 of these corners when moved 1 time also has to have no net twisting effect. And that is why twist is constrained. Now, I said that there was sort of, this was only true when the length of the cycles matched the order of the puzzle, or matched the order of the moves on the puzzle. So let's see why. If we just ignore this pentagon, this centerpiece on the pentultimate, let's do that. We'll just ignore what happens to this centerpiece on the pentultimate. Then we know that a face move is order 5 on this puzzle, and we know that the centers get permuted around in a 5 cycle, a cycle of length 5. Then we would say, okay, well then twist is conserved for these centers. And that's not actually true. Twist is not conserved for these centers. And the reason that twist is not conserved for these centers is because there is a center that's being twisted in place. It's not part of a cycle of length 5. It's part of a cycle of length 1. And so we can't look at what happens after 1 move and say that's the same thing as what happens when we apply that 1 move 5 times. Because there is, I'll just draw this out. Probably only have to do this once. We'll draw it on a cube first. Right, so there's, the cycle of these corners, and they go around 4 times. But there's also a centerpiece in here, and it's going around on itself. So the original sort of criteria was that we know that something, when applied 4 times on this puzzle, goes back to nothing happened. But we have the same sequence being applied to it 4 times. And so really, it could be being twisted in, something could be happening to its twist after each move. And we just know that after 4 moves, there's nothing happening to its twist. But since its twist is also modulo 4, that sort of doesn't help us. It doesn't really prove anything. And that's effectively why there is no twist constraint whenever you have a piece that is sort of coaxial with a face. And what I mean by a piece that's coaxial with a face is a centerpiece. And so on, oh, where is the puzzle? Here it is. Right, corners, they get twisted this way, and that the axis that they get twisted on is sort of, you know, this way, and that's not coaxial with any face, you know, axes, but it is coaxial with a vertex axis. And so it's really when pieces are coaxial that, you know, there is no twist constraint. And so I have a two-dimensional puzzle here. And the reason I bring up a two-dimensional puzzle is there's a question of, do the axes just have to be parallel, or, you know, or do they truly have to be coaxial? And they truly have to be coaxial. And so we can ask ourselves for these pentagon pieces. So there's a pentagon piece here, pentagon piece here, pentagon piece here. You can sort of see kind of a pentagon piece here. There's some bandaging that's occurring on this puzzle. Is it possible to twist this piece in isolation? And the answer is no. Or, you know, any piece like it in isolation. Right? There is a twist. Twist is, or total twist is conserved on this puzzle. And the reason for that is effectively the same reason as on the Rubik's Cube, which is that when we turn this around, you know, it's all order 5 or modulo 5. When we turn this around, it's back into its position. No twist has occurred onto it, and therefore sort of 1/5 turns. I think that's a 1/5 turn. 1/5 turns also bring it around in a 5 cycle, and twist is conserved. And that would only not be the case if this piece were sort of in the center. And so even though all the axes on all these circles are all parallel to each other, they're sticking out towards the camera, because they don't actually, you know, lie on top of each other, they're just parallel to each other, twist is still conserved. And so you might ask, well, what about hybrid puzzles, or puzzles that are not the Rubik's Cube, or not the Megamix? What about things like the helicopter cube? Is twist still constrained on the Rubik's Cube? Put it another way, is it possible to have a corner twisted in isolation on this puzzle? And the answer is no. And let's look at why. You know, so let's see, does the criteria or the constraints hold? What is the order of an edge turn? Well, it's order 2, right? So you do it once, and then you do it again, and nothing has changed. And what is the length of the cycles of the corners? It's also 2. It's a 2 cycle. And since the order of the move and the length of the cycle is the same, we can say that twist is conserved for these corners. One interesting thing to point out here is that if we say, you know, if we label this edge as 0, we say that the corner is not being twisted. Well, the corner was not twisted here, so to get it back, it can't be twisted. So this also has to be a 0, you know, for total no net twist. But if we say, you know, this is a +1, the corner is being twisted clockwise as it goes from here to here, then we have to say that the corner is being twisted counterclockwise as it goes from here to here, right? And so there has to be a balance. You know, if on this puzzle, if we label, you know, an edge as a 0, then the other edge has to be labeled as a 0 as well. And if the edge is labeled as a 1, then the other edge has to be labeled as a -1, so that you know, when you apply the move twice, it, you know, comes back. That's just definitions. And again, as we sort of established in the beginning of the video, the definitions are effectively arbitrary and they're all sort of relative. But what matters is that because we know that, you know, when you apply, you know, the move that you have the same number of times as the order of the move, in this case 2, and because the pieces are in 2 cycles, then each individual move can't change the overall twist. Even if it changes this corner to be turned clockwise, then this corner had to have been turned counterclockwise so that the total twist is still constrained at 0. And so let's talk about another puzzle, a much bigger, much more complicated puzzle. And we can, so here is one of the types of moves on this puzzle. And there are 5 corners on this puzzle, and I think you can see, I'm not going to do it, but I think you can see that the order of this face turn is order 5, and these corners move in a 5 cycle. It's the same length, and so if we look at what happens to each corner after one move, we know that that's the same thing as looking at what happens to one corner after 5 moves. And since we know that after 5 moves, one corner is not twisted in place, then after one move, the net effect on 5 corners is also that there is no extra twist. And so twist is constrained for the corners of this puzzle. The same argument goes for these edges, but the edges are now more complicated. So we have edges being moved in 2 5 cycles. We have these 5 edges, and we also have these 5 edges. And it doesn't matter that 10 edges are being moved in one move on this puzzle, because we can just look at each cycle individually. We know that, as we track what happens to this edge as it gets turned around 5 times, we know that it will be, after we turn this 5 times, it'll be back into its original position and its original orientation. Nothing will have happened to it. And therefore, if we look at what happens to this edge, this edge, this edge, this edge, and this edge, after one move, we also know that no net twisting will be possible even after a single move. Now, there are additional moves on this puzzle. So there's an even deeper move here, right? So there's and this puzzle is quite challenging to turn, right? So there's this slice move, and this slice move moves 5 corners. But because this slice move is also order 5, and these corners are in a 5 cycle, we know that there cannot be any net twisting effect. If we look at what happens to each one of the 5 after one move, that's effectively the same thing as what happens to one corner as it moves around 5 times. And since we know that one corner moved around 5 times doesn't twist, then the total net twist on 5 corners after one move also has no net twist. And there are no edges being moved in this particular slice, but there is yet one more slice move on this puzzle, and it is that one right there. And this slice move permutes 10 edges. And these 10 edges are actually permuted in 2 5 cycles. And so let me show you what those 2 5 cycles are. So we have this edge piece and this edge piece. And as we look through a move, so there's one move, those 2 edge pieces that were here go to right there. And so we actually have sort of 2 interwoven 5 cycles. I'm going to try to draw that for you. So let me erase my whiteboard here, and I will try to draw that for you. It's not going to be the best thing or easiest thing for me because my handwriting is terrible. But we have a pentagon, like, oh boy, that's a bad pentagon. Right, so we have a pentagon like that. And so we have, this edge, 1, 2, 3, 4, 5. So we also have another, so that's 1 5 cycle. We have another pentagon, which is kind of like that. And so this is, we'll call this A, B, C, D, E. We have 2 5 cycles. They get turned together. And so even though we have these 2 5 cycles, even though the 10 pieces are being moved, we can just decompose this into its 2 5 cycles. We can look at what happens to each one of the 5 pieces in each one of the cycles after one move. And because we know that after we turn this 5 times, one piece will be back in its original spot, unchanged. We can look at what happens to the other 9 pieces as we do one move and decompose them into their 2 individual 5 cycles. And we know that, there is no net twist that occurs on any of those pieces. And so it's really the fact, it's really just the fact that turning something 4 times, or in this, on a puzzle like this, 5 times, turning a face the same amount as its order is a null operation. It's a no-op, or it's an identity operation. It's as though you turn to nothing. And because you have these 5 cycles, or these 4 cycles, or the cycles that match the order, you can look at what happens to each of the 5, or each of the n pieces on an order n move, and determine that there's a twist constraint. And so on a hybrid puzzle, again, you could do that analysis on the corners, and you'll see that Rubik's Cube moves, they don't break the twist. They conserve twist. But these corner turns, they do violate this twist constraint. So it is possible to have a piece affected on this puzzle. And I've got another puzzle over here. So here's another hybrid puzzle. So this hybrid puzzle did violate the twist constraint. And that's because the corner piece is coaxial with the move itself. And so that means that the corner moves on a 1 cycle. And so twist is not constrained. This puzzle turns like a Rubik's Cube. But it also turns like a helicopter cube. And so then the question is twist constrained for the corners on this puzzle? And the answer is yes. And we really just need to make sure that this property holds for both types of moves. So we can look at the corners. And this type of move is of order 4. So when we apply it 4 times, all the corners are back into the original position in the original twist. Nothing has occurred. And because they're in 4 cycles, we can look at what happens after a single move. And the net twist that occurred for this corner, this corner, this corner, and this corner also has to be, net no change, even if individual pieces are being twisted. So the constraint is held for the corners when applying face moves. Is the constraint held for the corners when applying helicopter moves? And of course, as we saw in the helicopter cube, the answer is yes. A helicopter turn is of order 2. And the cycle of the corners is of order 2. And so when we track what happens to one corner when applied twice, we know that nothing occurs to that corner, is the same thing as when we look at the 2 corners after one move, when we know no net effect could have occurred in total for those 2. And therefore, for both types of moves on this puzzle that move corners, namely face moves and helicopter moves, we know that since both of those preserve the total twist of the corners, then for the entire puzzle, no matter what combination of moves you perform, the total twist must be preserved. So I hope that was an intuitive understanding of why twisty puzzles have constrained twist, why this seems to be such a universal property, and the only times that this property are ever sort of violated are for centerpieces. They're for pieces that move in 1 cycles. So, I know it was long, and I know I rambled, and I know I said the same thing over and over and over, and I probably misspoke a couple times, but I hope that if you sort of work through all the details in your head or work through all the details on paper, you'll see that sort of this intuitive way to think about it is actually sort of formally correct, that it really does prove that twist is constrained. And it basically does so in a way that doesn't involve a lot of heavy lifting, a lot of complicated mathematics, a lot of complicated group theory terms like group homomorphisms, or the wreath product of the corners being permuted around the puzzle, or anything like that. So if you have any questions please let me know in the comments on this video or on the Twisty Puzzles forum, or just message me, and we can try to discuss it. We can try to hash it out. But I hope you've come away from this video sort of feeling more comfortable about this whole conserved twist idea and sort of have an intuitive understanding of why it comes about. Thank you for watching.